Yeah, thank you. So, yeah, my name is Khurram Naeem. So, I'll today talk about, not working. So, I'll today talk about undersea sensing with Bristlemouth systems. So, yeah, we got the project recently. I'll go over the project's overview, and then, yeah, my name is Khurram Naeem. I'm working in University of Pittsburgh as a research professor slash.
Just needed a little encouragement.
So optical sensing, optical fiber sensing particularly, and instrumentation. So yeah, how we'll use Bristlemouth system in our project. So I'll just go overview of that project. So yeah, basically, I just gave a brief overview of what we are doing and what our expertise have. So we are working with fiber optic sensors research for diverse sensing applications. So it typically involves actually this oil and gas pipeline, transportation system, civil application include roads and bridges, electricity, grid monitoring, and other renewable energy generation system monitoring. So yeah, we are developing basically, our goal is to develop intelligent infrastructure sensing system, which includes the fiber optic sensors, modalities, instrumentations, integration of the data with the machine learning and AI framework. And yeah, the core competencies lies in actually we are monitoring both the static and dynamic parameters, excludes the strain, temperature, vibration acoustics, and other biochemical. So yeah, this is what so basically we are focusing on two technologies. So it's hidden actually in here. So we are working in the OTDR technologies, which we are developing for long range, long haul communication or sensing, particularly 10 kilometers to 40 kilometers and so. And at the same time, we are developing some frequency domain technologies, which are low range, 100 meters, but it has a very high spatial resolution in the millimeter or centimeter range. Yeah, so going to that, so what we done so far, so we developed a lot of interrogation system. It includes ultrasonic acoustic sensor system, FPG interrogators, relay-based distributed acoustic sensor, relay frequency domain, OFDR technology, and then at the same time, we are using commercial sensing modalities as well. I won't go into detail. Yeah, this is what some of the applications that ultrasonic acoustic can do. We perform a lot of field testings. We use interrogator FPG for lithium-ion battery. And this is our some Southwest Research Institute, Texas. We perform distributed sensor for pipeline monitoring, actually, some of the strain and temperature at different locations. So, yeah. Yeah. So this is a project, actually, I'll just go overview. We are, so far is our collaborating partner. So last year, we got this project, hybrid distributed pH, CO2 temperature and acoustic sensing for marine environment monitoring. So the main goal is to monitor the carbon dioxide and other parameters. So I'm not the marine science guy. So I'll focus on the sensing side actually. So the goal of that, the summary of that project is to develop a marine rugged size distributed fiber optic sensors integrated with commercial marine sensing platform like the SOFAR ocean buoy system. So new distributed chemical sensing, optical fiber sensing equipment, that can measure pH and CO2. Integrated technology combining data with temperature, pH, CO2, acoustics, and final deliverable is about the complete marine buoy multi-parameter distributed temperature, acoustic, and chemical sensing, platform or system. So the proposed targets actually includes, so if you look at the state of the art and if you go to our one, so distributed pH and sensing done over hundreds of meters probably. Our goal is to increase the range of the sensing of the pH 5 to 9, special limit actually. We want to go kilometer depth in the ocean. So kilometer sensing fiber would go under the ocean and where every meter would act as a sensor. So in 1 kilometer, so every meter, so this means 1,000 sensors are serially multiplexed. So every 1 meter, we will get the information about the whatever measurement we are interested in. So pH, CO2 similarly, 100 to 3,000 ppm, and again 1 kilometer range. Hybrid distributed sensor system, temperature and acoustics both. Temperature. This is a state of the art, but we are going at least 3 parameter, temperature, acoustic, pH, CO2 is Acoustic is not sure at the moment, given the limitation with some other marine sensing platform, actually. Yeah, so the end goal is low cost, low power, compact marine deployed, spatially distributed multi-parameter fiber optic sensor system. Yeah, I forgot. So yeah, I just give a brief summary of the goal that we have to achieve, actually. So here is the ocean spotter buoy system that is responsible for powering up the interrogation system and, of course, the communication. Yeah, this is what we are doing, actually. So the interrogation system that we will develop mostly would be custom design that would be housed in a waterproof casing underneath the float, power up by the buoy platform, and yeah, responsible for the pH over a kilometer range underneath. So here we see the optical cable. So yeah, we are looking at least 500 meter to 1 kilometer range, where every meter would be a sensing. We don't need separate interrogation system. There would be a one laser source and one detector. Please remember that. So yeah, so optical fiber cable at the same time would be a sensing cable, would be a data line as well. So it would be a typically remote sensing. So transmission signal, the light transmitted, cable will perform the sensing, and the same cable we will retrieve the data from the same sensing cable. So yeah, one just single optical fiber cable would be a transmission would be done through. Sensing would be done, and of course, the data line, it would be a data line as well. So yeah. So yeah, key innovation actually at the moment we have to make actually, so yeah, a hybrid distributed fiber optic sensor technology that would be able to monitor at least 3 parameters of interest. So acoustic is a challenge at the moment. We can perform the acoustic sensing, but the integration and is a pretty costly actually. So we at the moment is not in the question actually. So yeah, so another is new chemical sensing layer. We are collaborating with NETL laboratories. So where we develop optical fiber is not sensitive to chemical. We need to engineer a material polymer layer outside the optical fiber cable. So that material actually acts as a that introduces transducing effect in the optical fiber. So it interacts with the CO2 material properties changes that modulates the signal in the optical fiber, and that's where we get the sensing, data. So yeah, we are already engineering these material polymer layers in our lab, and the two graduate students are working on that. So one is for pH and one is for CO2. They are testing. We are looking for low-cost interrogation system with optical fiber and Bristlemouth system. And of course, here we are our collaboration is going on with the SOFA team. And last one is just engineer a hybrid sensing cable which protects actually all the cables, optical fiber cables for CO2, pH, and temperature in just one single cable. You can see here 4 cables. Red, and so yeah, that goes underneath the ocean, and yeah, so it should be protected from the harsh conditions of the ocean. Yeah, so overall project, product technology vision is that there is a SOFA a spotter buoy system, and next is actually our optical fiber sensing interrogator comes in. So it has an interrogation system plus the optical fiber sensing cable. So yeah, optical sensing involves these two things. I gives more. So yeah, we are developing a customized hybrid distributed sensing solution which enables simultaneous monitoring of distributed temperature and chemical parameters. So yeah, 3 parameters, measurement range, 500 meter to 1 kilometer, and 1 meter is spatial resolution. Every 5 to 10 minutes, data sampling is very high. That is spatial sampling. That the 50 mega sample means 2 meter spatial resolution, and 100 mean 1 meter. Power consumption. There is actually the main. So we want 30 watt at least. So at the moment, the Bristlemouth system provide 10 watts. So yeah, we need at least 20 to 30 watt to enable our sensing. And we have to manage actually strict swap conditions. So we have to, and this is our system. So we will use some commercial platform. We will value add. We will customize, and we will be able to get to, actually the system is tested already in the laboratory, but we also propose this for this project as well. So yeah, temperature sensing, and yeah, addition is we will make it a hybrid actually sensing solution. So simultaneous, two parameters are surely here, CO2 or pH, and yeah, if this system has one more channel, so we can make it at the same time. Otherwise, we have to go one by one here. So first CO2 cable through actually switch, we will connect the CO2 optical fiber cable and then with the pH. And yeah, temperature is every time. So we'll make it temperature is continuously. So yeah, thank you very much. I'll just go to.
Hi, everyone. My name is Michael Bella. I'm one of the EEs here at SOFAR. Because of time constraints, I'll be covering my stuff tomorrow in a breakout session instead. So come find me then if you'll be around.
Yeah, if you're interested in higher power.
Yep. Higher power for Bristlemouth is the main topic.
There's some people, there's some nods.
Okay, good, good,
Got
good.
some takers.
We'll have a crowd. Cool.
Great, thank you, Michael. Yeah. Everyone says that.
No pressure, no pressure. Okay.
Okay, so thank you guys. I mean, if they left it up to me, we'd be here all night. Well, I would be here all night. If you want to have, maybe not everybody caught that in remote land, but tomorrow, Michael will be leading a breakout session in design for higher power for Bristlemouth. So if you're interested in that, that'll give you an opportunity to sit. It's unstructured, so I'm not going to come tell him to here at time. So it'll be plenty of time to work with you guys. So if I know you'll be there.